In this video, we're going to be taking a look at software patterns and pattern-based design. The core idea here is that we can speed development and produce a high-quality product by taking advantage of proven solutions for common design problems. Each of us has likely encountered a problem, software-related or otherwise, and thought, has anyone already developed a solution for this? Is there a standard way to describe this problem so I can check if a solution already exists? Or if a solution does exist, how can I tell if it's appropriate for my needs? How do we know if we're poorly trying to reinvent the wheel here when a refined solution already exists that we could just apply to our problem? Well, design patterns offer a potential solution to these problems. Design patterns offer a method for describing problems and their solution that allows us to build large collections of patterns for common problems. These repositories of patterns enable us to easily evaluate potential solutions for our applications that have already been proven to be effective in real-world use. I have a quote here by Christopher Alexander that sums up what design patterns are fairly well. Christopher Alexander was an Australian-born British-American architect, but not an architect of software. He was an architect of buildings, towns, roads, and so on. He first described design patterns in his 1997 book, A Pattern Language. He noticed that there were commonly occurring problems in building architecture that would benefit from well-designed generic solutions that could be applied to most cases where these problems tend to pop up. This quote originates from his book and is considered to be the start of the pattern language movement. It reads, "Each pattern describes a problem that occurs over and over again in our environment and then describes the core of a solution to that problem in such a way that you can use the solution a million times over without ever doing it the same way twice." Alexander's ideas were later translated into the software world, and today we now have dozens of pattern repositories for all kinds of common software problems. All of that's great, but what is a design pattern? Well, a design pattern can be thought of as a rule which defines a relationship between a certain context, problem, and solution. Context allows us to understand the environment and scenarios in which the problem exists, and what solutions might be appropriate. Context also tells us about the software domain the pattern applies to. This is one of the reasons why it's important to identify and understand the software domain of your project. Let's now jump right in and take a look at an example. This search box pattern comes from an example in your textbook and defines a solution to the problem of users needing to find a specific item on a website. The solution is a search box UI element, and the context is web development, specifically navigation of a website. There's no one accepted standard for documenting patterns. Many repositories have their own templates, but most contain the information shown here in one form or another. We'll get into the details about what each of these fields means in this template soon enough, but for now, at a high level, this pattern describes the search box UI element that's commonly used on websites. At the top here, we can see we have a definition of the problem. In this case, it's trying to find a specific item or information on a website. Next, we have a context that explains the environment the problem and solution exists in this case, web development and UI navigation. We also have a very detailed solution that has a proven track record in real-world use, including basic examples. Here we see a description of the search bar, how it works, as well as a screenshot of an example. We also have consequences listed here, and these are the potential trade-offs for using this solution. For example, complex search results from a search bar can increase the user's memory load, especially if it's the only way to navigate the site, and this can also lead to accessibility issues. And the last items we have here are real-world uses, as well as related patterns. Related patterns is very important because it can help us find alternatives that we could consider, as well as patterns that are complementary to this one. So what makes a good or effective design pattern? How do we know if one pattern is better than another? Well, all effective design patterns should have the following characteristics. Number one, solves a problem. Patterns should capture a specific solution, not just abstract principles or strategies. Two, a proven concept. A good pattern should capture solutions with a proven track record, not theories or speculation. Number three, the solution isn't obvious. If the solution's obvious, there's no point in writing it down. Number 4 describes a relationship. Pattern gives a deeper description of a system structure and mechanisms. Should be clear what the impact on the system will be and what considerations need to be made. Lastly, a pattern should be elegant in its approach and utility. It should be described as a simple solution to a specific problem. It should appeal to both aesthetics and usefulness. Overall goal of design patterns is to save you from reinventing the wheel, or worse, inventing a new wheel when not necessary. That's the overall goal, so if a pattern does that, it's at least working towards achieving that goal. There's quite a variety of different patterns and types of patterns that span different application domains, level of abstraction, and approaches. I have just a few possible categories of patterns listed here, but there are many, many more. We'll now take a closer look at a few of these. So first up are architectural patterns. These describe the high-level and broad-based design problems that impact the system's overall architecture. They impact multiple system components and describe how the components are related and collaborate with one another. The example pattern shown here lines up with the architectural styles we covered in our video on architectural design and includes patterns such as client-server, peer-to-peer, or microservices. If you want to know more about those, make sure you review that video on architecture. Next up are data patterns. Data patterns describe data-oriented problems and the data model solutions that can be implemented to solve them. If you recall from previous lectures, a data model is an abstraction that shows and organizes the elements of data in a system and how they relate to each other. One example of a data pattern is the shared data pattern, where multiple components access data through a common data store or database. Another example of a pattern would be CRUD, C-R-U-D, which stands for create, read, update, and delete. These each define 4 different ways in which data may be accessed or manipulated. CRUD is a common pattern in both web development and databases. For example, in web development, it would be post, get, put, and delete, whereas in SQL, it would be insert, select, update, and delete. The last example pattern we have here for a data pattern is CQRS, or Command Query Responsibility Segregation. This is a design philosophy that states that every method should either be a command that performs an action or a query that returns data to the caller, but not both. The next category of patterns are component patterns. This is what most people think of when you talk about software patterns, and they are frequently just called design patterns in literature. I should also point out that there is some overlap in these categories. Many of the other pattern categories we'll be talking about also fall under component patterns, or can be seen as a specialized type of component pattern. Component patterns address problems associated with the development of subsystems and how these components communicate with one another. You can think of architectural patterns as describing what components are going to exist in your system, whereas component patterns fill in the details that are specific to each one of those components in the overall architecture. Next are interface patterns. These address common user interface problems and often deal with different UI controls that might be appropriate in specific contexts and for certain end users. The example now shown here on the screen is the password strength meter pattern. You may have seen something like this before when signing up for an account. Based on the complexity of your desired password, different password strengths are displayed. Here are 2 more examples of interface patterns. In the navigation tabs pattern, a tab-based design is used to progressively display information or UI controls as they're needed to not overload the user with everything all at once. This is commonly used in web browsers to allow users to quickly switch between different web pages they might have open. We saw the search bar pattern previously, but again, this UI controls allows users to quickly search for a specific item or information. It works best when paired with other navigational tools, so users can both explore and find the information they need, as well as jump to a specific page if they know what they're looking for. Web application patterns are specific to the problems encountered in web development and incorporate elements of patterns from other categories, usually interface patterns. The example shown now is for the product page pattern. This comes from uipatterns.com and describes the problem of how best to inform a user of a product's details on an e-commerce site. The solution is a page specific to the product with related information grouped into chunks with common design elements, such as a product title, a picture of the product, add to cart button, and so on. You've likely encountered this pattern in real life when shopping on Amazon or other e-commerce sites. Here's how this pattern would be described in the uipatterns.com repository. First, we have a summary of the problem, and then a real-world example, in this case from the e-commerce site Uniqlo. Next, we have a description of how the pattern is used and more examples. For this pattern, it says the product page is used to display information about a product in an e-commerce site, on a manufacturer or brand website, product comparison website, or other product-centric websites. Next, we have a more detailed description of the solution, as well as common elements involved in the solution, such as an add to cart button, and optional elements such as wish lists, zoom functionality, availability, and so on. We're also given a rationale for when this pattern should be used and the context it exists in, and some discussion about the different ways this pattern can be implemented and other patterns and techniques it's used with. The idea with patterns is not to give you code or a low-level solution, but a generalized or high-level solution that can be tailored to your specific needs. Lastly, we have sources or citations, and even more examples, and related patterns. Having knowledge of what other patterns exist for a similar context or domain is extremely helpful while weighting alternatives or finding complementary patterns. Another example of a web application pattern would be the shopping cart that's common to e-commerce sites. You're probably pretty familiar with this if you've ever done any kind of shopping online, but the idea is the user will add items to their cart before eventually checking out. Another example from social media would be the following and follow feature that allows you to follow other people as well as other people to follow you. Next up are mobile patterns. This category of patterns describes solutions to common problems encountered when developing mobile applications, typically for phones and tablets. Shown here are some common mobile patterns. Again, there is some overlap here with interface patterns, but there are a lot of unique characteristics to mobile computing that have to be accounted for. Some examples would be a touch-based interface rather than mouse or keyboard, a smaller screen size, which means less screen real estate to work with, and an operating system design that tends to favor one application being used at a time, rather than having multiple windows with different applications. The last category of patterns we'll be taking a look at are object-oriented patterns. These patterns are far more low-level and relate to how we design object-oriented components and code. These patterns tend to fall into three subcategories: creational, structural, and behavioral. Creational patterns focus on the creation, composition, and representation of objects. Some common examples of creational patterns are the abstract factory and the builder pattern. The abstract factory pattern allows you to produce families of related objects without specifying a concrete class. By factory, we mean a class or object whose primary purpose is creating objects of another class. The idea here is that using a factory rather than a class's constructor allows for polymorphism for object creation, not only object use. This provides further encapsulation and prevents code from being tied to a specific object or class, making it easier to refactor or redesign components in the system without impacting other code and reducing dependencies. The example that we currently see on the screen is from the refactoring.guru pattern repository. It's given as an example of the abstract factory pattern. In this case, we can see that we have an interface named GUI factory that is implemented by the Win factory and the Mac factory. The idea here is that the Win factory is used to create UI elements when the application is run on a Windows computer, and the Mac factory is used on Mac OS. The working of both of these factories are abstracted away from the application, which only requires knowledge of the methods provided by the GUI factory's interface and the generic interfaces for each control, such as a button as is shown here. Another example of a creation pattern is the builder pattern. The builder pattern allows us to build a complex object step by step, rather than in one constructor call. This is especially helpful when the object is complex and requires the initialization of many fields and nested objects. The solution is to use builder objects that handle the construction of a new object part by part or step by step. In the example currently shown on the screen right now, also from refactoring.guru, a builder interface provides methods that are common to all builders, and the implementing builder classes provide concrete implementations for a specific product. A product in this case being the resulting object that is being created. These products don't necessarily have to belong to the same class, interface, or hierarchy, and the director class here defines the order in which to call the steps in a given builder object so that you can create and reuse specific configurations of products. For more details on creation patterns, see the creation patterns section of the refactoring.guru site. They do a great job of explaining these in simple terms with multiple examples and diagrams. The next subcategory of object-oriented patterns are structural patterns. These focus on problems and solutions associated with how classes and objects are organized and integrated to build a larger structure. Two common examples of structural patterns are the adapter pattern and the container pattern. The adapter pattern describes how objects with incompatible interfaces can collaborate. For example, maybe we had a class that deals with XML. We might use this adapter pattern to also make it support JSON. So here's a somewhat silly example, again from Refactoring Guru, of the adapter pattern. In this instance, we have a round hole class that tells us if an object of the round peg class will fit in a given instance of the round hole, based on the peg's radius. However, we also want to be able to use a square peg and see if that square peg will fit through that hole. In theory, a square peg can fit through a round hole if the square peg is small enough. But the fits method of the round hole class only takes a round peg object. So what can we do here? Well, to make it also accommodate a square peg, we can create a square peg adapter class, which is a child of the round peg class. Thanks to polymorphism, this means that objects of the square peg adapter will also be accepted as round pegs in the fits method. That means we could also pass these to the fits method. The square peg adapter takes an instance of square peg and calculates a radius that this square would fit through as the return of getRadius. This allows us to use this object with the round hole object and its fits method. For more examples of structural patterns, check out the structural patterns section of the Refactoring Guru site. They also go into a lot more depth on these two patterns that we took a quick look at. The last subcategory are behavioral patterns. These address problems associated with the assignment of responsibilities between objects and the manner in which communication is effected between objects. Two common examples of behavioral patterns are chain of responsibility and the command pattern. In the chain of responsibility pattern, requests are passed along a chain of handlers. Each handler processes the request and passes it along the chain. This is a common approach in server applications when handling user requests. Each handler decides whether it can process the request. If it cannot, for example, maybe this user isn't authorized to perform this request, or there's missing information, then the handler rejects the request and does not continue sending it down the chain. This pattern is also occasionally used the opposite way, where a request will only be dealt with by the first handler that can process it and only passed on to the other handlers if that handler is unable to fulfill the request. This is common when dealing with events in stacks of elements within a graphical user interface, for example. The next example is of the command pattern. In the command pattern, requests or commands are turned into standalone objects that contain all the information about the request and how to execute it. This allows you to pass a request as a method argument or to create a queue of the requests for later processing. One common use is to make operations or actions undoable, as is shown here. In this example, we have a command class that defines a number of common attributes and operations for all commands in a text editor, and each specific command, such as copy, cut, paste, and undo, extend the command class. Most importantly here, each command has an execute method that performs the command and an undo method that undoes it. This enables a command history object to keep a history of all of the commands issued to date in a stack and for them to be applied or undone using the execute or undo methods. If you're interested in learning more about these patterns or behavioral patterns, again, I would recommend Refactoring Guru as a good starting place. Now that we have reviewed a few patterns and pattern categories, how do we find and learn about new patterns? Where do patterns come from? Well, obviously, they're created by someone. Individuals and organizations often keep track of successful techniques they've used in the past projects and document them for use in future projects. The next source is from pre existing books or catalogs of patterns. There are many such books, mostly focusing on a specific category of pattern, but perhaps the most famous and influential is Design Patterns by Gamma, Helm, Johnson, and Velistes. These four authors are often known as the Gang of Four or GOF, and the book really initiated the concept of design patterns in software development. Next are online repositories such as uipatterns.com. These sites function in the same way as books, offering a detailed catalog of design patterns, typically from a specific category of patterns or for a particular application domain. Lastly, and this is somewhat of a new area in software engineering, is discovering new patterns through machine learning. The idea being that we could discover new and novel patterns by analyzing past successful software projects and using machine learning techniques. So, the most common way you will likely access patterns today is through online repositories. Many of these exist, but I have a few examples here that are free or at least offer some of their catalog for free. If you're new to patterns, especially object-oriented patterns, I highly recommend refactoring.guru. They have many examples of each pattern, illustrations, and explain them in some simple terms that are very accessible to beginners. If you're looking for something more specific to a specific domain or a specific category, some of the other ones here are really useful, like uipatterns.com for user interface patterns. So, how do we document a pattern if we have found a proven solution that we want to share with others? Well, as we've seen, there is no official standard template, but we do have one that's suggested by our textbook. We saw an example of this earlier for the search bar pattern, but this is the generic template. At the top, we have the pattern's name, something to uniquely identify it. The next row is for a description of the problem that's addressed by the pattern. Aliases or other names the pattern is known by. The motivation for the pattern, this is typically an example of where or when this problem occurs, and a rationale for the proposed solution. The context this pattern exists in, this would be a description of the environment and application domain the problem resides in. Next is a list of forces that affect the problem and how we may choose to solve it. This should include a discussion of the limitations and constraints that must be considered. For example, with the search bar pattern, this would be the forces such as if the website already has primary navigation, if users want to search for an item only in a specific category, or if users want to use Boolean operations in their search. All of these would impact how we implement the solution proposed by the pattern. The next row would contain a detailed solution to the problem, ideally with examples and even screenshots. Intent describes the overall goal of the pattern and what it does at a high level. Collaborations lists other patterns that are related to or part of the solution described in this pattern. Consequences lists the potential trade-offs of using the solution described by the pattern and the consequences that could have on your overall architecture and component design. For example, for the search bar pattern, one potential consequence would be that if only a search bar was used, some parts of the site would only be accessible via the search box, and this may be hard for new users to learn or navigate between pages. This lets us know that if we use this pattern's proposed solution, we should probably also consider including a second means of navigation that allows for discovery of new pages. Implementation identifies any special issues or details that should be considered when implementing the pattern's solution. Known uses gives references to real-world applications that have used this solution successfully. Remember, patterns should always be proven in real-world use. And lastly, references to related design patterns in the catalog or repository are listed to help find alternatives or complementary patterns. There is one more category of patterns I should mention, and those are anti-patterns. Unlike design patterns, anti-patterns describe commonly used solutions to problems that have a negative effect on software quality. This means using solutions described in this pattern would hurt your software application rather than be beneficial. Now, why would we want repositories of anti-patterns that describe a poor or bad solution? One of the main reasons we might want a catalog of anti-patterns is to help developers recognize when these sorts of problems exist so they can avoid them and implement better solutions to these problems. We can sometimes learn best from seeing examples of what we should not do. Next would be to provide guidance during refactoring. Identifying use of anti-patterns in our own codebase allows us to target areas that might need to be refactored to improve quality. Remember that refactoring is the process of going back to old code and improving its design, structure, efficiency, or style without changing its overall function. Lastly, anti-patterns can be used during technical reviews to identify areas of concern or issues that need to be resolved before design is approved or code is committed. Let's now take a look at a few well-known anti-patterns. The first is the blob. This is an object-oriented design anti-pattern that describes a developer placing far too many attributes and operations in a single class. Remember that classes should have a single theme or topic, and only contain attributes and operations that are directly related to that topic. This is what we call cohesiveness. Classes that follow the blob anti-pattern would have low cohesion and could cause issues such as being too complex for reuse and testing, or it could become too expensive to load into memory due to excessive and unneeded resource use. Here's an example of how we might document this anti-pattern. It's similar to the template we saw for patterns, but focuses more on the symptoms, consequences, and causes of the anti-pattern. The described solution is focused on resolving or correcting inappropriate patterns and how to avoid its reoccurrence. Our next anti-pattern are stovepipe systems. This is an architectural anti-pattern that describes systems that have the potential to share data or functionality, but do not do so. One example might be having components with a different username and password for the same users. This obviously would be extremely frustrating and annoying for users of the system, as they would have to memorize multiple accounts and passwords just to use one system. The name stovepipes here is a reference to old stoves that had pipes rising out of houses and above buildings, each functioning completely individually with its own stove. The boat anchor anti-pattern refers to keeping part of a system around even though it no longer serves any purpose, sort of like a boat anchor slowing down a boat. This is commonly code that no longer has any purpose or use, but can also be documents and other work products created during the modeling phase of a project that are never updated or used. Next is spaghetti code, and spaghetti code refers to programs whose structure is barely comprehensible due to misusing code structures or failing to follow some sort of consistent style or design philosophy. This is often a result of another anti-pattern called cargo cult programming, which describes a programmer copying and pasting an example code from different sources, maybe online from something like Stack Overflow, without having a good understanding of what each line in this code actually does, or what its function is. This leads to a mess of spaghetti code that's hard to understand, debug, test, or document. Next up is copy and paste programming. This is closely related to cargo cult programming, but involves the programmer copying and pasting their own code without any alterations or just minor alterations, rather than creating a generic solution, such as a method or class, that could be reused. Not only does this reduce reusability and create more spaghetti code, it also makes testing harder as there is more code to test and makes future updates more difficult, as there will be more lines of code to change. The silver bullet anti-pattern describes the assumption that a popular technical solution will always solve a larger problem. This can occur when a certain technical solution gains popularity in industry such as cloud computing, machine learning, blockchain, NFTs, or so on. These technical solutions are not necessarily bad on their own and often have appropriate use cases in certain contexts. But the downside here is when we see them applied when inappropriate or harmful. The issue here is that a more traditional or simpler solution would work just the same or likely better, but we are using this more advanced or complex solution simply because it's the current buzzword in the industry. The last anti-pattern we'll be looking at is programming by permutation, another pattern that's closely related to cargo cult programming. In this approach, a developer starts with some code they wish to change or add new functionality to, and does so not by understanding the code and planning out their modifications, but randomly changing parts of the code and seeing if it works. This leads to spaghetti code and results in code that the developer does not understand, which will make future maintenance and bug fixes really difficult. It also often leads to less efficient code, as the approach being taken could be redundant, poorly optimized, or not take advantage of language-related features. Now that we know about patterns and anti-patterns, how do they fit into our design process and development activities? Here we have a diagram from our textbook that visualizes part of the process model centered around pattern-based design. The process starts with a requirements model. As we've already covered in previous lectures, requirements model is an abstract representation of the system that describes the problem, context, and any forces that may impact the project. Once design begins, 3 important actions must happen. Design concepts have to be considered, the problem's context and forces must be defined, and we have to contemplate what quality attributes and non-functional requirements will be important. We'll be talking a lot more about quality attributes in a future lecture. Based on our understanding of the problem and the context it exists in, we then evaluate if a pre-existing pattern addresses our problem. This is accomplished by referring to relevant pattern repositories and comparing the problem and context described in the pattern with the problems we are attempting to address. If the design seems appropriate, you incorporate that pattern into your design. If no pattern fits your needs, or this is a novel problem, you would use traditional design methods and notations we've already covered in past lectures to create a solution. Lastly, as with most processes we have seen in this course, we need to evaluate our work. In this case, we need to reevaluate our assumptions about the problem set, context, and forces, and evaluate if the proposed design and use of patterns is appropriate. Throughout this whole process, we should always be looking for opportunities to apply existing patterns that meet our needs. This saves us time on design work, improves quality by using a proven solution, and prevents us from reinventing the wheel. The last thing we need to cover in this video are common design mistakes when working with patterns. The first, and by far the most common mistake, is simply not taking enough time to understand your problem or the pattern you have selected. This leads to adopting a pattern that is inappropriate. Next is to keep trying to use the pattern you selected erroneously, as you refuse to see your error and attempt to force that pattern to fit your problem. This often causes more harm and more work overall than simply designing your own solution or taking the time to find an appropriate pattern in the first place. Another possibility is that our problem has forces or context that's not considered by the pattern, making it a poor fit. This is why it's so important to understand the context and environment our problem exists in before selecting patterns. Lastly, sometimes we select an appropriate pattern but apply it too literally. Patterns are meant to be generic, high-level solutions that can be applied to many systems. They often need some customization or adaptations for your specific problem and context. That's all I have for you in this video. If you're just getting started with patterns, I highly recommend checking out some of those free online repositories to get a better idea of what's available and how these patterns are documented. UI-patterns.com and refactoring.guru are great starting points for beginners, and I highly recommend checking them out. Thank you for watching, and have a great day.